Welcome to Avesha's demo, where AI-first scaling meets resilient GPU orchestration. In this video, you'll see how Avesha's platform brings together observability, automation, and intelligence to supercharge your Kubernetes workloads. What you'll see in this video: benchmarking, predictive smart scaler versus standard HPA for LLM inference, demo of smart scaler improving CPU-GPU inference performance, demo of EGS elastic GPU service across multi-cloud clusters, AI workload prioritization and eviction to reclaim GPU capacity, automated failover and recovery from GPU node loss. Benchmarking, predictive smart scaler versus standard HPA for LLM inference.
Avesha's Kubernetes portfolio uniquely brings infrastructure and application observability together with automated scaling and right-sizing for both CPU and GPU workloads. Let's look at how Smart Scaler improves scaling and performance of inference endpoints. In a standardized test using sinusoidal traffic towards Llama 3 8B model, compared to using standard HPA, an increase in batch size resulting in higher instantaneous throughput using Smart Scaler was observed. When using standard HPA, the sum of peaks of the batch sizes was 47 and improved to 87 when scaling was switched to Smart Scaler. That was an 85% improvement. It was also observed that the max tokens per batch improved from 12,580 to 21,955, roughly 70% improvement. As a result, the request process per unit time improved from 292 to 413, a 40% improvement, as well as tokens processed per unit time improved from 72,000 to 104,000, a 31% improvement. Similar results were also achieved for the Deepseek 7B model.
Demo of smart scaler improving CPU-GPU inference performance.
Uniquely brings infrastructure and application observability together with automated scaling and right-sizing of both CPU and GPU workloads. Our AI-first approach to workload characterization and scaling uses infrastructure telemetry data such as CPU, memory, GPU temperature, and application telemetry data such as traffic, error rates, time to first token, max tokens per batch, max batch size, to determine the scaling properties of a pod, as well as that of any related pods to determine the real bottlenecks. The metrics data paired with Insight Smart Scaler extracts is presented in an intuitive, easy-to-use dashboard that puts actionable information for applications across the Kubernetes footprint. It provides capabilities to drill down from the enterprise to the cluster level, to the application level, as well as all the way to the microservice level. And it surfaces trouble spots to focus on, as well as wastage in allocated resources and its actual utilization. It is also great with identifying and fixing applications that are over-provisioned and wasteful. Now let's look at a Grafana dashboard to see how Smart Scaler improves scaling and performance of inferencing endpoints. In this charts, the first two cycles of the test represent when the inferencing endpoint is scaled using standard HPA, and the cycles after represent the inferencing endpoint scaled by Smart Scaler. You can see the drastic improvement in request latencies from when using standard HPA versus when using Smart Scaler, as well as reduction in number of waiting jobs between standard HPA and Smart Scaler, as well as time to first token and the reduction in queue time.
Demo of EGS across multi-cloud clusters, AI workload prioritization and eviction to reclaim GPU capacity.
We're going to have a demo here of Avesha's Elastic GPU service. This is a service that manages GPUs at scale and inferencing endpoints at scale that run on top of those GPUs. So I'm going to start by grabbing my token and logging in. This is all Kubernetes based. This infrastructure runs on top of a Kubernetes cluster that may be hosting GPUs. The first thing you'll see is as we drop into our dashboard is that we have a couple of GPU clusters already here loaded in the system, and that's hosting about 6 total GPUs, and some of these are being used. You may notice off on the side of the screen there's some batch inferencing that's running in the background on some GPUs that we have deployed already, but we'll get back to that. As we look at the GPU inventory, the first thing that will pop out is that we're actually looking at multiple clusters here. We're seeing both GCP clusters and Oracle Cloud clusters that can be managed seamlessly within the same environment with EGS. And you'll see a few different shapes show up, the node types that are underlying seeing those clouds. This really, again, very Kubernetes focused. It's cloud-agnostic, but you can see that we do have multiple clusters running. The primary management paradigm for EGS is using workspaces. Think of a workspace as a team or an area or a space like a workbench where you may want to put a bunch of GPU resources for that team to utilize. So we make it very simple to set up a different, we call it a slice or a slice workspace. Look at maybe a team that has built a sales agent helper that's using some inferencing endpoints to maybe grab information for sales agents who are trying to work with customers and so forth. And there's a staging version of this, and there's a production version of this. And you can see these both have access to both clusters, so there's lots of resource available. And then we maybe have some VLLM scaling jobs running on the side, and this is really only available on Worker 2 cluster, which is over in Oracle Cloud. To see where these inferencing endpoints are set up within these workspaces, we're going to navigate over to the inferencing endpoint area and we'll dig into the staging one first. So you can see that the staging workspace already has an inference endpoint deployed. If we click into that, we'll see that everything's healthy. Everything's ready across the board. It's been assigned to an A10 GPU. So that's all good to go. And then if we look at the production endpoint, again, very similar. Everything's ready across the board, good to go. This one happens to be assigned to an A100 over in the GCP cluster. So staging on Oracle, production on GCP. Now, one thing that may happen, or tends to happen, can happen. Sometimes we'll see GPUs kind of disappear, especially if you're using spot instance. So I'm going to actually go ahead and start scaling down that A100 node that's running production. This could just go offline on its own. I'm kind of forcing the issue just by terraforming that one down. And that'll take just a couple of minutes while that's scaling down. So I see it looks like our production has gone down. So that does not look good. If we went then back to our production inferencing endpoint, we may see that it's gone offline. Well, at any rate, we know the node's on the way out. It's no longer functioning as an inferencing endpoint. And we need to kind of get things back up and running pretty quickly. Because it's a production service. So rather than, now we're not ready, so we see that outright that it's not ready. Rather than trying to fix this A100, probably a better choice is let's just use a backup over on Oracle Cloud. So production is running in GCP, but there's no reason we can't switch clouds and run this agent somewhere else. So we'll do a sales agent over on an A10 in Oracle Cloud, which happens to be Worker 2. We'll use a Llama 3. This allows full custom models to be dropped into here. So we'll just grab a Llama 3 model spec that will allow this endpoint to scale up quickly. We'll pick that A10 GPU. We just need one node, and let's just do it for a couple of days. Hopefully our production system will be back online in a couple of days. Now, one thing you may have noticed is our GPU inventory on Oracle is already fully allocated. So I'm going to put this at a high priority because we want this to override any other jobs that are currently running. So as I create that inference endpoint, you'll see that it's going to queue that into the creation process, and that's going to be off and moving. Has a number of GPUs being provisioned. This is the new GPU request. We call this the GPU request screen. You can see that high priority coming in, and you can see that it's queued to get put into production. And that'll just take a minute as actually this VLLM job was running, and it's getting cycled out because it was on at a lower priority. So we're seeing that one sort of getting cycled out. And now our production is provisioned, which means that GPU has now been allocated into the production workspace. We should start to see our nodes and pods scale back up for that. So if I go over to my Oracle cluster, production sales agent, we can see this one is still on the way up. So that node is still doing its thing. I'll actually just kind of look at it in Lens since we're over here on Oracle. Find that production sales agent A10. which is this guy. It's currently container created, so we should be able to see logs on this to see how the Llama 3 model is coming up. Looks like we're up and running now. So now we should see that come back online. Let's see if the endpoint is back. We see that the production and inferencing batch is up and running again. We can see that confirmed if we look at the endpoints in the production area that the original one that was in GCP is no longer ready. The one that is moved on to Oracle Cloud on the 810s is now all provisioned and up and running. That bears out as well if we look at the GPU requests. We'll see that production, because of the high priority, was able to kick out the lower priority VLLM job that was running, which now that VLLM job is just erroring out because it's no longer working. That's kind of when we turn the A100s off. This job got scaled down. Well, not scaled down, but kick off the GPU because it was lower priority, and that GPU was made available for production inferencing, which we see that spun back up. Lastly, the GPU inventory has been updated. The dashboard reflects that updating by only having 4 GPUs available, and still reporting on the jobs that are currently running, temperatures on now both on those Oracle Cloud GPUs, and the utilization.
GPU cost analysis, track spend, allocation, utilization, and wastage.
We'll give a quick preview of the latest version of our EGS dashboard cost analysis. Cost analysis is helping IT teams and DevOps keep track of how much they're spending and the value that they're getting out of their infrastructure. Our dashboard keeps track by workspace, by workload, provides cost trends and different categories of cost. If we look at the cost and utilization tile and the wastage tile together, this gives a picture of what many CIOs may be facing in terms of underutilization of resources. The total GPU cost for this time period selected was $350. And what we found was that the allocated GPUs really accounted for about $60 of that spend. That's what actually got allocated into jobs through the workspaces, leaving $290 of GPUs unallocated. To dig a layer deeper, even of that $60 that was allocated, it was a very low utilization. So out of the entire $350 of allocation, really only 24 cents was utilized in this scenario. So something certainly people want to have an eye on and get those utilizations up, load balance workloads into nodes like this so that they can get much more cost effective and a return on the investment that they've made.
Let's recap what we just saw in this demo. Avesha delivers the intelligence, automation, and observability to make Kubernetes GPU workloads fast, resilient, and efficient. What we showed you: Smart Scaler, delivering lower latency and higher throughput for inference. How standard HPA falls short in dynamic traffic scenarios. EGS managing GPU clusters across Oracle and GCP. High-priority AI workloads evicting low-priority jobs in real time. Seamless failover from GCP to Oracle Cloud during GPU node failure. For more details, please go to www.avesha.io. Thank you.